Hi, in this video, we're going to provide a brief overview of our paper named Multi-Path Neural Networks for On-Device Multi-Domain Visual Classification. Learning multiple domains with a single model is an important topic for improving data efficiency, while positive knowledge sharing and lowering inference cost when running multiple vision tasks jointly. This is especially important on resource-constrained devices like mobile. However, handcrafting a multi-domain model can be both tedious and challenging. To solve these problems, we propose a novel approach to automatically learn a multi-path network for multi-domain visual classification on mobile devices. We named it as MPNAS. Second, we propose an adaptive balanced domain prioritization algorithm to achieve balanced performance on multiple domains simultaneously. Extensive evaluation demonstrates that the proposed MPNAS achieves the state-of-the-art performance in terms of accuracy, model size, and flops on MobileNet V3-like architectures. The proposed MPNAS approaches learns a cross-domain parameter sharing strategy to encourage positive knowledge transfer and also mitigate negative interference by using domain-wise path selection. In the figure, different color paths represent model architectures for different domains, and paths that run through the same node end up sharing the weights as shown by the dark gray node. The final model is formed by merging all the selected paths into a single network. The proposed multi-path network is learned from neural architecture search by applying one reinforcement learning controller to each domain to select the best path in the super network. At each search iteration, an RL controller samples one path from the super network to form a sampled model. All the sampled models are trained using a single batch of training images from each domain. Afterwards, the weight of RL controllers are updated using the accuracy on validation set as the reward. At the end of the search phase, we merge the output paths from each RL controller into a single joint model. The joint model is then trained from scratch using training data from all domains. Handling domains with diverse difficulty is another challenge in multi-domain learning. To solve this problem, we propose an adaptive balanced domain prioritization method called ABDP to achieve balanced training performance for all the domains. Instead of directly optimizing the sum of losses, a function h is introduced as a transformed objective function to boost the loss and therefore the priorities among domains. We evaluate the multiple options for the boosting functions and find that our exponential functions performs the best. Intuitively, the derivative can be viewed as the weight for domain DI, so domains with higher loss will result in higher weights. This means more challenging domains will be given higher weights during optimization. Finally, it balances the performance across domains. We performed extensive experiment on the visual domain Decathlon dataset and apply MPNAS on top of MobileNet V3-like search space. The table in this slide demonstrated the accuracy for different approaches on the visual Decathlon dataset. The first line of the table shows the baseline of running NAS on each single domain and then blindly bundling the models. Compared to SDNAS, MPNAS reduced the model size and flops by 78% and 32% respectively. MPNAS even shows a slightly increase in average accuracy over SDNAS. MPNAS also outperforms the state-of-the-art approach like the TRL network and etc. The table in this slide shows the ablation studies on the effectiveness of ABDP. Generally, applying ABDP on the top of various approaches shows consistent improvement in terms of average accuracy. Here is an example of search architecture produced from MPNAS. Green and red path show the selected path for the DTD and ImageNet. Dark nodes are shared between the two domains, while light nodes are independent. Intuitively, more correlated domains should share more nodes in order to maximize the positive knowledge transfer. We computed the pairwise Jahad similarity score and find that the paths for similar domains will indeed be more similar. To sum up, we propose a multi-path neural architecture search approach as the first work of applying efficient NAS to solve the challenges of on-device multi-domain learning. Second, the proposed ABDP algorithm can effectively optimize the model performance when training on multiple domains simultaneously.